Hey y'all, welcome back. This is video 3 of 3 for organometallics. Thanks for letting me kind of work my way through history and some of these metals. It's just a good idea to see all of them and see what they're doing and why we're even tortured by learning them. Not tortured, they're pretty fun. I want to tackle carbines. Now this is an OChem 1 topic. We'll see these in our pericyclic reactions, but if we're following along into history, we're getting into really ideas that started pretty early on for some of these, but the actual metals used weren't until the 1950s. So 1958, we went from the 30s to the 50s here with some more metals. And for the carbene that we're going to look at for the Simmons-Smith reaction, we are going to look at zinc. Okay, so we've looked at magnesium, copper, lithium, we've palladium, we've had some different metals. Our carbene reaction that we tend to see is with zinc. And what's cool with this is it's really quite specific. So we're going to take a methane only, not a normal methane. This is diiodo methane, 2 iodines on there. And it turns out if you treat this with zinc will do an insertion just like magnesium and lithium. The trippy part is if we look at the oxidation numbers for zinc when it forms ionic bonds, it's a +2, not a +1. So it actually inserts into this compound not once, but twice. And then what it does is it literally takes iodine. It strips off iodine, but it leaves behind, it only needs 1 electron from each iodine, and it leaves behind the other electrons in the bond. So you make the funkiest looking carbon ever because you leave behind the electrons on carbon. And what you form with your zinc is zinc iodide. Nice ionic compound. What is this carbon here? Okay, don't show my Gen Chem 1 students because I don't want to grade a Lewis structures exam and have lone pair on carbon everywhere. This is phenomenally rare. This is very specific. And this substrate is called a carbene. Isn't that cool? You could imagine that that's crazy reactive. I mean, you're really missing 2 bonds in your carbon, so it's quite reactive. There is no charge here. This is not a carbanion or a carbocation. Carbon started with 4 electrons. It still has 4 electrons. It's neutral. It's just crazy reactive. And what it's known for, this carbene does a pericyclic reaction. Now that will be a unit for us, part of our unit 4 for my OChem 1 class. Our pericyclic reaction is very specific with an alkene. And what happens is those 2 electrons in that carbene will form a ring with the 2 electrons in our alkene. Pericyclic means they happen all in a ring. And we just made, this is your carbon from your carbene right there, and you just made a cyclopropane. In my OChem 2 class, we've talked about making rings. And if we're doing something like an aldol, we can make a 5 or 6 membered ring quite quickly, a little bit of heat, and that is really quite preferred. But as we discussed, the other ring sizes have to have some help. You need a little bit of help to make those. Typically, your cyclopropanes, you need a little bit of help to make them, but then they're not too bad to make. So this is by far still used, and one of the best ways to make cyclopropanes out there is to use a carbene. Awesome. All right, so then let's work our way into a little bit more modern metals. Why I feel really strongly we have a little bit of metals in our background is starting in really the 1970s, organometallics exploded. It wasn't just insertions anymore. Now we're talking coupling and cross-coupling reactions. So we've got 3 that have now won Nobel Prizes within our generation. We've got the Heck reaction, let's draw that out, the Sonogashira reaction, and then Grubbs catalyst as our most recent. All 3 of these and various, there's lots of cross couplings. We're just picking these three because we see them in our Organic 1 and Organic 2 topics, but these have now won Nobel Prizes. Look at this. Heck just won a Nobel Prize with Suzuki and Negishi couplings in 2010. This is the next three are coupling reactions, and they're really sort of a version of a metathesis reaction. And these are like double displacement reactions back that you learned in Gen Chem. These are just the organic version, not just the inorganic version. Our Heck coupling reactions are going to use a palladium catalyst, and it's pretty cool. Starting in the 70s, he started taking substrates, specifically an alkyl halide, so something with some kind of alkyl halide on it. Benzene rings tend to work really well. So OChem 1, this is going to pop up in Unit 5. You can use this for synthesis. And then actually with some sort of double bond. And any kind of double bond, you can couple these using a palladium catalyst. So he tends to use a version of palladium that either has a chlorine on it or an acetate on it, some version of palladium for that Heck coupling. And it's just like our Gilman. We literally take the carbon attached to the alkyl halide, and we take that double bond right here, and you literally stick them together. That's the point of a coupling reaction. So now you have that coupled together. You just took this carbon and you just coupled them. You stuck them together. And what Heck is really good for, and what Heck is really known for, is this cross coupling. You know, you'll notice that my two partners were different. You can have a nice alkyl halide here, any kind of olefin there, or alkene, and you can stick those together. So for my OChem 1 class, this is going to be awesome on your synthesis in Unit 5. You can use these coupling reactions to make somewhat complex materials pretty straightforward, all just with using that palladium catalyst, either one of those. So then Heck coupling actually went through lots of different iterations. They all involve palladium somehow, but Suzuki's use boron also. I mean, there's lots of different coupling partners for those. They are still modern and they are still used today. In fact, in my Create group, my honors group, OChem 2, we were using and doing Suzuki couplings last semester with our boron and our palladium, and they were working quite well. So that's awesome. And then a Sonogashira coupling. We're only going to do two more, so I don't want to get you too saturated with your metals. Get it? That was a little metals joke. All right, with our Sonogashira coupling, also in the 70s, this one is pretty fun because we're also taking another alkyl halide, some kind of alkyl halide, only this time we're going to couple it with an terminal alkyne, okay? So we can couple these together also using palladium catalyst. But here's what's fun. We're about to combine that with some copper. You actually need the combination of palladium and copper for your Sonogashira to work. And then what happens is you literally are about to couple the carbon, that terminal carbon on your alkyne with your alkyl halide. And you can couple those together. And now you end up with a nice substituted alkyne, and you just coupled these two together. You're also welcome to use this OChem 1 Unit 5 synthesis. You can use your Sonogashira coupling. As far as the specifics on the catalyst, it's been around for about 30 years, so there's versions of palladium and copper. You just need to tell me palladium and copper. You don't have to have specifics. And then let's save the best for last. Let's do a Grubbs. Grubbs is awesome. Won the Nobel Prize in 2005. Grubbs is still here. Grubbs has a company in California that actually sells the Grubbs catalyst. There have been 2 generations of the Grubbs catalyst, and typically the second generation or first generation is what they're called. And Grubbs catalyst is awesome. It is known for 2 different things. It is known for something, just a coupling. And what's phenomenal is we are about to couple just two olefins or alkenes together. And what's fun on the actual catalyst is that you can take terminal alkenes, and you notice for the first time there's no alkyl halide here. We literally have an alkene terminal here and terminal here. That's important. What does terminal mean? You only have H's on the end. Grubbs catalyst is so modern, and it's so famous because you don't have an alkyl halide there. You just have two double bonds. And what happens is that Grubbs will insert here and insert here, and it will do the organic version of a double displacement reaction, which is called a metathesis. So you can stick those two together right there. Now notice that we are missing these two carbons. Why it's called a double displacement is literally the Grubbs catalyst will take on and insert both of these. You'll insert both of these compounds, so literally here and here, and then it literally displaces both, and you do a little do-si-do there, and you end up with this carbon attached to this carbon, and then your byproduct has those two terminal carbons stuck together. So your byproduct is always ethylene gas. You know when Grubbs is working because you're going to give off ethylene gas if you can trap that or have a way of knowing that that's leaving. So you do have to be careful with Grubbs because you are going to lose that end carbon on each one of those, and you're going to end up connecting your two internal carbons there on a Grubbs catalyst. Still known today. And then there's another iteration of Grubbs catalyst that we're going to use in class in OChem 1, and it's so awesome because we will learn in our pericyclics how to make our ring sizes, and we know from OChem 2 that ring sizes are pretty difficult to make. 5 and 6 membered rings are easier to make. But in our OChem 1, using Diels-Alder, we can only make a 6-membered ring. So what is Grubbs good for? It is good for making, let's see if I can draw this nice. Okay. It is good for making other sized rings. So let's try and use Grubbs here. And let's see what ring size we're about to make. Remember, you cut your terminal and you attach those other two carbons. So this is a great way of making 5-membered rings. We just attached these two carbons. We just lost ethylene right there. There's our ethylene gas. That's from this carbon and this carbon. So Grubbs, when you close a ring like this, is called a ring closing. Metathesis. And this is a great way to make rings of different sizes. So we can make a cyclopropane now, we can make cyclopentenes, and then we'll also do a Diels-Alder to make cyclohexenes. So we've got all different ring sizes. Grubbs is by far our most modern in our metals and our couplings, and it is fair game to use in synthesis. You don't need to tell me generation 1 or generation 2. Now we're getting really specific. You can say Grubbs catalyst. The metal in Grubbs catalyst is ruthenium. So we're getting into some other metals there. So this is the first time we've seen ruthenium, and this is the first time we haven't needed an alkyl halide. So Grubbs catalyst is famous because it closes rings like that. It's also famous because it's quite shelf stable. You can buy it in a jar and stick it on your shelf, and you can put two alkenes together. It's pretty awesome. So I hope this gives you some idea of what metals are good for, and in any of my synthesis or take home, if you want to use any of these metals for OChem 1 or OChem 2, you are more than welcome to do that. Just specify which one you're using, and we'll see bits and pieces of this in all of our units 4 and 5 for both OChem 1 and OChem 2. Awesome. So this is going to be the end of our organometallics.